Okay, so let's take a look at this sample problem. Okay, it says a plastic rod have a uniformly distributed charge. Negative Q, the rod has been bent in a 120-degree circular arc of the radius R. So this one, this is the center, and then this is a part of a circle. So it's a circular arc, and then this degree is this angle is 120 degree. Okay, so I have a uniform distributed charge, negative Q. And actually, even though when we try to derive this equation to consider that all the charge are positive, and if this is negative, it is okay. You just need to plug in the negative Q here, then all the thing will be the same. So here, the rod has been bent in the, we have a coordinate axis such that the axis of the symmetric of the rod lies on the x-axis, which means that this is positive 60 degree, negative 60 degree. Okay, and the origin is at the center of the curvature T of the rod. So in terms of Q and R, what is the electric field E to the rod at point P? So rather than a full circle, full ring, then we only have a part of the ring. So in that case, we really need to use the integration rather than just a multiplication. So here, it is like we try to separate this arc into many small segments. So for this one, ds. Okay, so this is ds, and then of course this is x-axis, and then we try to find the coordinate system so that this part and this part is asymmetric to the x-axis. So for this ds, you can, or maybe I should say for any ds, you can always find a symmetric part over the x-axis. So this is ds prime, which is symmetric to ds. And of course, the total charge is negative q. So we should have a q equals this, the length of this one. This is 120 degrees, and the full circle is 360 degrees. So it is 1/3 to the full ring. So it is like 2 pi. Is it r, or this is small r? 2 pi r over 3, and then times lambda. So rather than 2 pi r times lambda, because this is not a full ring. Okay, so here, for this ds, it is a negative charge. So dE points to this charge packet. So dE points to the upper right. And then it can decompose it in the y-axis and x-axis, like this. And then for the symmetric part, ds prime, the E field is pointing to the bottom right. And of course, this dE and dE prime has the same magnitude, but of course the direction are different. And after decomposite, dE prime on the y-axis and z-axis, the y-axis component cancel each other. So the remaining component is the x-axis component and point to the right side. Okay, so here we consider theta is this angle. Theta is this angle. And then, of course, this is considered to be 0 degree. So up to this part will be negative 60 degree, and up to here will be positive 60 degree. So later on, when we try to integrate the theta, then it is from negative 60 degree to positive 60 degree. Okay, so here, EE will be 1 over 4 pi epsilon naught. This is K, nothing special. And then times lambda times ds. also the same because dq is nothing but lambda times ds. Lambda is the linear charge density times the length of the small packet. Okay, and then over small r squared, because in this question, the radius of this arc is the small r rather than capital R. Okay, so here we consider the x-axis component. So dEx will be 1 over 4 pi epsilon naught times lambda ds and then over r squared. And then here, this is theta. So this one will be cosine of theta, because this one divided by this one will be cosine of theta. So we need to multiply cosine of theta here. Cosine of theta here. Okay, so so here we need to do some change of variable, because as I mentioned, we would like to integrating it for the degree rather than ds, because if it is ds, then yeah, we are not easy to express it. So here we need to do some change of variable. So it is like ds equals r d theta. Of course, this one is like the polar coordinate, 极坐标 polar coordinate. So in the polar coordinate, of course, usually you are familiar with the Cartesian coordinate, 直角坐标系 coordinate. But here it will be more, the calculation will be easier if we try to calculate it in the polar coordinate, because it is like a circle. So in a polar coordinate, we try to express a point with the distance r and also the theta. So here we try to express ds on a circle. So I expect in high school mathematics, if you try to consider this ds will be like r times d theta. D theta will be this. Maybe I make it slightly larger so that you can see it more clearly. So if we try, like this. Okay, when you try to consider this is ds, and this angle will be called d theta. Yeah, of course, this angle should be very, very small, but I cannot draw it too small. So yeah, it looks like quite large, but yeah, this d theta is a very, very small angle, so that this arc is ds. And in high school mathematics, you know, ds should be r times d theta. Okay, so this is how we want to change the variable. So that we have d theta here, and then this is cosine of theta. Then we can do the integration. And of course, lambda and r square is not related to theta at all, because this is r axis and theta axis is are independent. Okay, so in this case, we have dex equals 1 over 4 pi epsilon naught times r lambda d theta. Okay, maybe we can just maybe can show you like this. So this is ds, this is r d theta, so you can see it clearly, and then over r squared and then cosine theta. Okay, so here we can also do some simplification. This r can be cancelled with this r squared, so it down to R in the denominator. Okay, so next, we can try to calculate the total E field generated by the whole rod from this small E field. So the total E will be integration of dEx over the whole rod. Maybe we can call it the L. So we can try to plug in this one. Try to plug in this one here. Try to plug in this one here. So it looks like 1 over 4 pi epsilon naught O times lambda over R, and then cosine of theta d theta. And then, as I mentioned, we need to write the lower bound and upper bound of this definite integral. It is definite integral. And just mentioned, it is negative 60 degree and positive 60 degree, but in calculus, we seldom use degree. Rather than that, we usually use radian for the angle. So we write it as negative pi over 3 and then pi over 3 for negative 60 degree and positive 60 degree. Okay, so here, this is a constant, which means that we can just factor it out like this, and then we integrate cosine of theta d theta from negative pi over 3 to pi over 3. Okay, so the antiderivative of the cosine theta is sine of theta. I think you should know about that. So it is pi over r and then times sine of theta evaluate from negative pi over 3 to pi over 3. Okay, sine of pi over 3 is square root of 3 over 2, and then sine is an odd function. So this one turns out to be square root of 3 over 2 times 2, which is square root of 3. So it turns out to be 1 over 4 pi epsilon naught times square root of 3 here, and then times lambda over r. And of course, lambda is not a given variable, so we need to change it back. And as I mentioned, we have this expression. Q is the total charge amount, and then lambda is the charge density. 2 pi r over 3 is the length of this circular arc. So which means that we can write it as lambda equals 3q over 2 pi r. Okay, and then we plug in this one to here. So we can write it as square root of 3 over 4 pi epsilon naught, and then times 1 over r times 3q over 2 pi r. So it turns out to be 0.83q and then over 4 pi epsilon naught, and then times we have 1 r and then second r, and then so it is r squared here. So this is the answer to this question. Of course, it still looks like the form 1 over 4 pi epsilon naught times q over r squared. Of course, it has an additional factor 0.83 here because it is not a complete circle, a complete ring. So it has some factor in the front. But actually the dimensions are actually the same. Okay, so any questions? Okay, I just write everything in the previous page. Okay, no question, and then we can move forward. Okay, so this is a quick checkpoint. So for the figure here show 3 non-conducting rods, 1 circular, 2 straight. It has a uniform charge of magnitude Q. So along its top half and another along is the bottom half. For each rod, what is the direction of the net electric field at point P? So this quick checkpoint lets you familiar with how we do the cancellation. We don't really need to calculate anything. We only try to familiar with how to do the cancellation of part of the component. Okay, so let me start from this one. I can do the first one first, then you can try to think about the second and the third one, and when I ask, you can try to answer in the chat room, then I can mark it down for the participation. Okay, so for the first one, this part is the negative charge. Okay, so for this one, you can consider the E field at point P will point to the top left for the negative part. Okay, and for this part, this is a positive charge, so we'll expect the E field at point P will point to the upper right. Okay, this is E plus. So it turns out these two add together, so the x-axis component cancel each other. And then finally, this is the total E field at point P, which will pointing to the positive y-axis. Okay, so hope you understand how to do this one. And for the second one, who can answer this one? You know the answer, you can type it in the chat room. Okay, positive x-axis. Positive x. So okay, so I think okay, so yeah, the first one is already correct. Although you add an additional question mark. Okay, so here for this part, it will generate E field point to this side, and for this part, it will generate E field point to that side. So it will point to the positive x-axis. Okay, so let me mark it down. Okay, and how about the third one? Okay, negative y. Okay, so yeah. Okay, so yeah, negative y direction. Yeah, you can do it quickly. So for this one, you will generate the E field point to the bottom right, and then for this part, it will generate the E field pointing to the bottom left. So the y-axis component cancel, and then it will point to this side. So negative y-axis. Okay, so let's move on. Okay, so this is another case, which is about the electric field due to a charged disk. Okay, just now we consider a ring. And here we consider the solid disk. You can see here the green one is a solid disk. And yeah, of course, we can try to separate the disk into small pieces. But as much as we already consider the charge ring, so we can try to separate the solid disk into into many rings with different radius, and then so on and so forth, and then it will, when you try to add all the ring together, then it will form a solid disk. The idea is like this. And of course, you may ask, if we don't know how to find the E field generated by the ring, what can it be? Maybe you can try to consider whether it's possible to try to cut the circle or cut the disk like this in the Cartesian coordinate. So it is like cutting the disk in the Cartesian coordinate. And I will tell you that it will be quite complicated for the calculation. It's just like when you have the calculus class, you try to calculate the area of a circle in Cartesian coordinate. It will be, at least the calculation is a bit complicated. You can write this part will be y equals square root of r squared minus x squared, and then the area will be, the area of a circle will be 2 times of a integration of square root of r squared minus x squared dx, and then from negative r to positive r. And then of course you need to do some substitution, like x equals r times sine of theta, something like that, to finish the calculation. So similar for this case, if you try to separate this into small segments along the xy axis in the Cartesian coordinate, the computation will be very complicated. But we can also try to cut this using polar coordinate, so that it will look like this. Then the computation will be easier. It's just like just now when we calculate the ring, we just fix the radius, and then we try to cut the ring along the theta axis, and then here we also integrate it over the r. So yeah, that's the point here. Okay, so it try to tell you that when you have a disk, and then you try to calculate the E field on this z-axis, the z-axis are similar to the definition for the ring. Except this is a solid disk, so actually the definition is the same for the z-axis. So the expression will look like this. And sorry, this is not the solve the E field for the disk. This is for the line of charge. This is for the line of charge, if you still remember, just a few pages before. So this is for the expression for the line of charge. And here we try to separate the ring separate the disk into many rings with different radius. So rather than writing it as capital R, we try to write it as small r, and then we try to integrate it over R. And then rather than calling it E, we try to calling it the E field generated by this small ring to be dE. And then this is Q, and then we try to call it dQ for a ring. And the other stuff are the same. So the difference is that we change E to dE, change Q to dQ, and then we change capital R to small r. Other stuff are the same. And here we don't try to applying z to be much larger than r yet. Otherwise, all the stuff will be the same. So and then it will give you incorrect answer. So far we don't try to consider the far field condition yet. we try to come up with a closed form solution, and then we try to apply the far field condition later. Okay, so here, this is the E field generated by a ring. Okay, so this is the same expression, and then we try to sum from 0 to R, which means we do the integration. But of course, before doing the calculation, we need to do some substitution, because this is dq, and we try to integrate from R. So we need to change the variable dq to be sigma times dA. Yeah, so here we have the ring, but we consider it has some thickness. So dA is the area. Is the area of this ring. Yeah. And sigma is the surface charge density rather than linear charge density here. Yeah, because if we still consider the ring is very, very thin without any thickness, then it cannot add up to be a solid disk. So here we still need to consider it has a small thickness. Okay, so from dq to sigma dA, I think it is still easy to accept. So this is the surface charge density. And one point to know is that the SI unit for the surface charge density should be C over meter squared rather than C over M. C over M is for linear charge density. So here C over meter squared is for surface charge density. Okay, so up to this part, I think it is easy to accept. And then for this part is related to the polar coordinate. Okay, so this is dA. So in the polar coordinate, of course, you have the r-axis towards different direction. And then when you try to consider the dA, this is dA, and you can consider this is r up to this point is r, and then this is dr, and then this angle is theta, and then this small angle is d theta. Okay, so in that case, this dA will be r times dr d theta rather than dr d theta. We need to have this one, because r times d theta, you can consider this one is a rectangle. Although this is not a rectangle, it's like a this does not look like a rectangle, but if dr and d theta is small enough, you can regard it as a rectangular. It's rectangular. So rectangular is like, this is the height, this is the width, and the width will be r times d theta rather than d theta, because d theta is just an angle. This is a length. So this is the width, r times d theta. This is dr. And then, yeah, so the dA will be, this is dr. The height is dr. And then this is the width, r times d theta. So this one multiplied by this one will be the dA. But here, this is 2 pi r dr, which means that we try to integrate. We integrate the theta. We try to integrate the theta from 0 to 2 pi for the whole circle. So we have RD. So this dA will be RD theta, and then integrate it from 0 to 2 pi. And then so d theta, and then RDR is independent to theta. So we will have d times dr times integration of 0 to 2 pi and then d theta. And this one is nothing but 2 pi. So it turns out to be 2 pi r dr. And this is what you can see here. So here so this dA consider the whole area for the ring. And of course this dA consider only this part, or you can consider it is only this part. Maybe I can call it dA prime here. This is dA prime, will be r times dr d theta. Okay, so integration of a dA prime over d theta, dA prime from dA prime from 0 to 2 pi will be this one, will be dA. Okay, so this is the substitution we need to do so that we have dr, and then we can integrate it from 0 to capital R. So this is the change of variable. And then we try to plug in this expression to here, so that you can see here we have a sigma 2 pi r dr, sigma 2 pi r dr, and then with this z to be here. And then of course this one is at the denominator. This is 1 over 4 pi epsilon naught. So this is the closed form for dE, and then we can try to do this integration. And here we try to do some cancellation, which means we try to cancel this pi with this pi, and then we try to put these two in the front. So we have sigma z here, and then we have 2r dr here. And the other stuff remains, this is 4 epsilon naught, and this one and this one. Okay, so we try to simplify the expression of dE, and then we can do the integration. So yeah, so the total E is integration of dE, so which is sigma z over 4 epsilon naught, and then we integrate the remaining stuff, which is related to R from 0 to capital R. Okay, so this integration is not so difficult because it is like the change of variable or for the chain rule, which means d r squared plus z squared equals 2r dr. Yeah, because z is a constant to r. C and r are independent. R is pointing to this side, and then z point to another side. So r and z are, so this is like a constant. You can regard it as dr, and then r squared plus z squared equals 2r. So take the derivative of r squared will be 2r, and then take the derivative of a constant will be 0. So look like this, and then you can going back to here. So it just multiply dr to this side. So we have this one equal this one, which means that 2r dr is this one. And then this one to the 3/2 power, which is this one in the denominator to the negative 3/2 power. So this is easy because this is like a polynomial with, of course, with a strange power. But this is not difficult because we just need to add 1 to the power and then divide this value. And this is the antiderivative of this function, because we already have the dr squared plus z squared here. This one and this one are actually the same. And then we try to evaluate it from 0 to capital R. So when we try to plug in, well, of course, we have a negative sign here. So we plug in z0 here. Of course, this is R to be 0 and R to be capital R. So when R to be 0, it is z squared to the negative 1/2. So it is 1 over z squared, take the square root. And then when we plug in small r to be capital R, we have a z squared plus capital R squared. Then take the square root, then with a minus sign. Okay, so it looks like this. And of course, this one is actually this one is 1 over z minus 1 over z squared plus R squared. Okay, so we try to factor out z. So, or maybe we can just distribute this z to here and to here. So this z and this z will cancel each other. So it turns out to be sigma over 2 epsilon naught to be here. And then z cancel with this z will be 1. And then z put it here. So we have a z over c squared over capital R plus capital R squared, and then take the square root. So this is the closed form solution for this disk. Okay, so the remaining stuff we consider is that if we consider R to be infinitely large, which means that this disk is infinitely large. We have an infinitely large charge plate. Then this one will be 0 because you can consider, let's say, this is infinitely large, which means that you can consider it like 1 over put it down R over Z and then square, yeah, something like this. So if R is much larger than Z, or R tends to infinity, so the denominator tends to infinity and the whole term tends to 0. So if R tends to infinity, this term vanishes, and it remains that E equals sigma over 2E epsilon naught. Maybe you will ask, how can we create an infinitely large charge plate? But yeah, of course we can, but later on in chapter 25, when we talk about the capacitor in chapter 25, we will use this expression frequently. Of course, it's just an approximation, but it is already good enough. But because we don't really need a very accurate expression. Yeah, and more importantly, when you look at this one, sigma is a constant. Epsilon naught is another constant. If you still remember, epsilon naught is 8.85 times 10 to the negative 12 power. Of course, with a complicated SI unit, but this is a constant. This is also a constant, and this is also a constant, which means that this is a constant. The whole thing is a constant. It is not related to the distance from the plate to the point you concern, which means that if this plate is infinitely large, it will generate a uniform E field in the whole space. But of course, even if the plate is not large enough, then if you consider the point close to this plate, then you can consider the E field are quite uniform. So that's the point here. So for large parallel plate, it will, or large charge plate, it will generate E field uniformly. So up to now, any questions? Okay, no question, then we can move forward. We can talk about this point charge in an electric field. Okay, so here it says a particle with charge Q is placed in an external E field E and electrostatic force F acts on the particle. So it is nothing special because at the beginning of this chapter, it already tells you that if you have a charged particle placed in an E field, then there will be a force. Or the definition is the other way around. You try to define the E field by the electrostatic force acting on this charge. So this is the definition. And then you try to multiply Q to the other side. So here it means that if you try to place a charge in the E field, then there will be a force acting on this charge. Okay, so making use of the parallel plate. So just now we have a single plate, and here we place a parallel plate with opposite side. For example, if we this one has a positive charge distribute on this plate, and then we have negative charge distribute on the bottom plate, then we can consider the E field. We can consider the E field between this parallel plate to be uniform, and of course pointing downward, because the electric field line is starting from the positive charge to the negative charge. Okay, so we usually consider the E field inside the parallel plate will be uniform, and then we usually try to neglect the E field out of the parallel plate, but of course it is not zero, but it will try to decrease when it is out of the capacitor, when it is far away from the parallel plate. But at least here in this course, we usually will ignore the so-called fringe. This is so-called the fringe capacitance, the fringe E field. Okay, so so here try to accept that there is a uniform E field pointing downward between the parallel plate, and here it try to introduce simply explain the mechanism for the inkjet printer. For example, if you have the green ink, you try to print it on the paper on different location, then you try to add some charges on this ink, so it becomes a charged particle. Of course, the charge will be negative charge because you try to add some electron on the ink. And of course, if the charge is negative, then the force will be pointing upward. The force will be pointing upward throughout the capacitor, throughout the parallel charge plate. Okay, so in that case, it is just like what you have learned in the if you have a initial velocity of v, and then there are some gravitational force mg, then it will look like a parabola. Yeah, it is the other way around, because we will neglect the gravitational force and the electrostatic force is pointing upward. So if you turn it upside down, it feels like you have this phenomenon. But of course, it is not the gravitational force. It is due to the electrostatic force. Okay, so to control where should you put the ink, then you try to change the charge amount on the ink, then you can change which point it projects to. So the input signal from the computer control the charge and thus the effect of the E field on where the drop lands on the paper. So this is the simple mechanism for the inkjet printer. And here we look at a simple sample problem about this one. So it says the deflecting plate of an inkjet printer with a superimposed coordinate axis. So the ink drop with mass, this one, and a negative charge of magnitude Q enters the region between the plate, initially moving along the x-axis with Vx. So we have a Vx will be 18 meters per second. So the length of the L of each plate is 1.6. So this L is 1.6 centimeter. Okay, the plates are charged and thus produce the electric field at all points between them, assuming the field is downward directed, uniform, and has magnitude. This one, what is the vertical deflected of the drop at the edge of the plate? The gravitational force on the drop can be neglected. Of course, when you try to calculate the gravitational force, it must be much smaller than the electrostatic force, as we have calculated something similar in the previous chapter. Okay, so here, when you try to consider this kind of problem, because the force are only in the vertical direction, so in the horizontal direction, there is no force acting on it, so the horizontal velocity doesn't change at all. Then you can expect the time it comes to here will be t equals to the length over by the velocity. So the length is 1.6 centimeter, but for the SI unit, we should convert it to 0.016 meter. Okay, so this is a 0.016 over Vx is 18 meter per second. Okay, so this one is 8.89 times 10 to negative 4 second. Okay, so this is the time this ink leave the parallel plate. Okay, so and then next we try to calculate F equals QE because we know the charge amount of the ink, and also we know the E field generated by the parallel plate. So we can calculate the electrostatic force. So Q is maybe we can write it as a capital Q to match with this one. So Q is 1.5 times 10 to negative 13 power, and then times 1.4 times 10 to the 6. Yeah, so this is 2.1 times 10 to negative 7 Newton. Of course, if you consider the gravitational force, mg, g is 9.8, or if you consider it as 10 meter per second square, so it is around 1.3 times 10 to negative 9 Newton. So it is much smaller than this one. Okay, so here y will be half of at squared, which is something like the high school physics. So I don't try to talk it detailedly. So 1/2 at squared, and then according to Newton's second law of motion, we have a equals F over m. So we have F over 2m t squared. Okay, so we can plug in the number. F is this one, 2.1 times 10 to negative 7. and then times t square is 8.89 times 10 to negative 4 quantity square over 2 times m. M is 1.3 times 10 to negative 10th power. So finally, this is 6.4 times 10 to negative 4 meter, or you can write it as 0.64 millimeter, or you can write it as 640 micrometer. And these are the answers. So in the exam, you can try to answer it in this way. This is the scientific notation. Something. This number should be between 1 and 10. Strictly less than 10 with only one digit. Of course, it can have a decimal value, but between 1 and 10 can equal to 1, but less than 10, and then multiply by 10 to a power. Okay, this is so-called the scientific notation, and this is so-called the scientific prefix. Of course, I expect you to remember the scientific prefix. The scientific prefix. Okay, so you can simply check it here. The scientific prefixes on the Wikipedia. You can, metric prefix. So of course you don't need to remember too much. I think up to giga, mega, kilo. H and DA, I don't think you need to do so. Kilo, mega, giga. I think when you use computer, you already know it very well. But for the smaller one, I suppose you know milli. I suppose you know milliliter, ml, or millimeter. And then micro is for 10 to the minus 6, and then nano for 10 to the minus 9, pico, and then femto. I think you need to remember these 4, just like for the milli, micro, nano, pico, and femto. This is 10 to minus 3, 10 to minus 6, 10 to minus 9, 10 to minus 12, and 10 to minus 15. So I suppose you should remember this few. And of course for kilo, mega, and giga, I suppose you already know it well. And okay, so let's stop it here today.